Marilyn purchased a mailing list of 20 names and addresses for her mail order business. But after scanning the list, she doubts the authenticity of the list. If 40% of the names on the list are non-authentic, calculate probability of selecting exactly 10 non-authentic names in her list. This is a typical binomial experiment. We have just two possible outcomes for this experiment, to be a non-authentic name or to be an authentic name. Because we are looking to calculate the probability to be a non-authentic name, probability that it's considered a success in this experiment is to be non-authentic, and this probability is given, it's 40%. The complement probability in this situation to be an authentic name is 1 minus decimal 40, so it'll be decimal 60. We have 20 names on her address, so the number of trials in this binomial experiment is 20. This is a formula that will give us the possibility to calculate the probability to have x times a success in a binomial experiment. So probability to have x times a success will be combination of n trials taken x at a time times probability to be considered a success at power x times probability to be considered a failure at power n minus x. It's n minus x because if we have x times a success out of n trials, we have n minus x failures. So for part A, we need to calculate the probability of having exactly 10 non-authentic names. So we're looking to calculate probability when x is 10. So the combination of 20, choose 10 at a time, times probability to be a success, decimal 40 at power 10, times decimal 60 at power 20 minus 10, 10. When we calculate this probability, we have decimal 1171, so 11.71%. So probability of selecting exactly 10 non-authentic names is 11.71%. For part B, we are looking to calculate the probability of selecting at least 2 non-authentic names on her list. So, what possibilities do we have to select non-authentic names? Can be 0 non-authentic, 1, 2, 3, 4, and so on up to 20. If I need to select at least 2, that means can be 2 non-authentic names on the list, 3, 4, 5, 6, 7, up to 20 inclusive. So too many probabilities to calculate. But we know that total probability is, for a probability distribution, is 1. So if we subtract from 1 probability to have 0 non-authentic name or 1, we have the probability to select at least 2 non-authentic names. So probability to have x more than or equal to 2 can be simplified as 1 minus probability to have 0 non-authentic names minus probability to have 1 non-authentic name on the list. So we can calculate these probabilities. So it will be 1 minus combination of 20, choose 0, decimal 4 at power 0 times decimal 6 at power 20 minus combination of 20, choose 1, decimal 4 at power 1 times decimal 6 at power 19. If we calculate this, we have decimal 99947. So it's almost 99.95%. So probability of selecting at least 2 non-authentic names is 99.95%. This probability can be calculated also using binomial tables. I choose the table for n equals 20 and we have it in front of us. Once more, all that we can calculate based on binomial tables is a cumulative probability for x less or equal a particular value. So, because I'm looking to calculate probability to have at least 2 non-authentic, I can do it as 1 minus probability when x is equal or less than 1, and I can use for this probability the table. So probability to have at least 2 non-authentic names is 1 minus probability when x equal or less than 1. Our situation in our diagram. So less than or equal to. So if we're looking at the table, I'm looking for a probability to be considered success 40%. So this one I'm looking here. Less or equal 1, we can see that is decimal 005. So it'll be 1 minus decimal 0005. So this gives me decimal 9995. So we can see that it's 99.95%, the probability that we calculated also based on our formula. For part C, they ask probability of selecting 5 or fewer non-authentic names. So I'm looking to calculate probability when x is less or equal 5. That one would be probability of having x equal to 5, probability x equal 4, probability x equal 3, and so on. So x is 1 plus, don't forget, probability when x is 0. We can see that it's a bit more to calculate. So we have in this equation to calculate 6 probabilities and put them together. We can do similar using the table. So less or equal 5 with a probability p decimal 40. So if we are looking at less or equal 5, so this is decimal 1256, so 12.56%. So the probability of having 5 or less than 5 non-authentic names on the list is 12.56%. Let's return to our questions. They asked to calculate what is the average, the expected number of non-authentic names in the list. For the expected value for a binomial experiment, the expected value for the mean is the number of trials times probability to be considered a success. In our situation will be 20 times decimal 4, so this will be 8. So the expected value for non-authentic names on her list is 8. So in average, I'd expect to have this number of non-authentic names on the list. Also, we have to calculate the standard deviation of this variable. The standard deviation for a binomial experiment is square root of n times p times q. Once more, n is the number of trials, p is the probability to be considered a success, and q is probability to be considered a failure. So if we plug in this formula, it will be square root of 20 times decimal 4 and times decimal 6. If we calculate this one, we have a standard deviation of 2.19. So in average, I will expect to have 8 plus and minus 2.19 non-authentic names on this list.